Okay, welcome to lessons 2 and 3 of energy and momentum. We'll go a little bit of graphing and then we will take a look at some more examples involving work and energy. So, interpreting graphs. We did a little bit of this in the chapter on kinematics. And you may have seen this in Physics 11. Some teachers cover it, some teachers not quite so much. But you may have studied in Physics 11, you recall that the force on a stretched spring increases as the spring is stretched. And so the force varies directly with the extension of the spring. Often we look at this just because as an introduction to graphing. So how this ends up looking is something like this, where we graph the force versus the extension on a spring. What we see for most of the spring itself is a graph that looks like this. Obviously, things get a little bit weird here at the end. If you pull the spring too far, if anyone's ever played with and broken a slinky, you'll see things get weird here when the spring gets too stretched. But what you end up with here is a linear graph. So we know the equation for this graph can be given to us as y equals mx plus b. Or in this case, the y-axis is our force. We have our slope, and then we have our extension here, which we call x. The question is, what does this slope here represent? And if you looked at this back in Physics 11, you'll have seen that for a spring, the force is actually equal to k times x, where k is what we call the spring constant, and the units for that are newtons per meter of stretch. So the slope here is equal to the spring constant. Spring constant K. So let's look at what this actually gives us when we graph this thing. So a spring has a spring which has a spring constant of 1.5 newtons per meter is stretched by 3 meters or stretched to 3 meters. And so we're going to graph this thing. So if there's no force on the spring, obviously it's not going to have an extension. So we can graph the point 0, 0. If the force is given by F equals kx, and we know that k is 1.5, we multiply that by our 1 meter extension, and we're going to get that the force here is 1.5 newtons. So this guy's going to be 3 newtons, this guy's going to be 4.5 newtons, and we can graph this thing. Here's my force. Here's my extension. The units of this are meters. This guy is given to us in newtons. Oh, sorry, I should get this up there for you. Okay, cool. So I've got my force in newtons, my extension in meters. So let's graph this thing. So 1, 2, 3, 4, 5. I'm going to have 1 meter of extension, and we're going to be here at 1.5, 2 meters at 3, 3 meters at 4.5. And so we can connect the dots, make our line. Get the blinds, hopefully that makes it easier. Actually, it doesn't. It makes it worse. No, forget it. I'll just move this over and hopefully get this video done before the sun moves too much further. So we've got we got this here. The slope of this is, slope is rise over run, which in this case is going to be the 1.5 newtons per meter, because this thing's going to go up 4.5 and over 3. 4.5 over 3 equals 1.5 newtons per meter. Now, so that's the slope. What about the area? So if we look at this graph, we can see that what we've got here is a triangle. So we're going to find out what the area of this graph is, and you'll see why we're doing this here in a second. So the area under that graph is given to us by 1/2 base times height. The base here length is 3. The height is 4.5. So if we multiply all these things together, we're going to get 6.75. But 6.75 what? Oh, sorry. I'll put this back over here. 6.75 what? So let's look at the units here. The base here is measured in, let's do that. The base here is measured in meters. Let's put that unit in there. The 4.5 here is measured in newtons. It's a force. So we're running at 6.75 Newton meters. We have seen Newton meters before. Newton meters is a force times a distance. So then what does this represent? Well, force times distance is work. So if we look at the graph of a force and an extension on for a spring rather, what we can see here is that the area under the curve is the work done to actually extend that spring. So this is useful. This becomes useful when let's write this down here. This is a useful way to find work. When the force is changing. Normally we have, so if we look at the expression for work equals a force times the distance, but what do you do if the force is increasing as you go? Well, then in this case you could graph it. If you graph it, you find the area under the curve. If you have done any sort of IB math or you've looked at calculus at all, you'll recognize what the area under, hopefully you'll recognize what the area under a curve is. The area under the curve is actually the integral. You're summing up the area underneath that curve. So we're integrating, which is cool, which we're not actually going to do here in Physics 12. But you can see where this is going, hopefully, for upcoming years. So let's do a couple examples of this before the sun completely overwhelms me here. Cool. Let's do this. There we go. Block out the sun. So by examining the units in the previous calculation, we can see that the area under the graph tells us the joules of work or the Newton meters of work done. Those are the same here. I'll grab another color. The joules of work. Also the Newton meters. Newton meters are joules. We like joules just because it makes it clear that work is an expression of a change in energy. So work equals the area under a force distance or a force displacement graph. So let's do a few of these. If we have a constant force with a displacement of 5 meters, this becomes relatively trivial. So we've got we got work equals a force times a distance. We know the force here is constant, so we could just say, okay, I've got a 3 Newton force acting over 5 meters. That's going to give me 15 joules of energy. Or we could use what we just looked at. We say, well, work is the area under an FD graph. Well, what shape is that? That is a rectangle. So in this case, we're going to have the area equals a length times a width. The length here is 5. The width here is 3, or vice versa. Either way, we're going to get 15. This is meters, this is newtons, so we get our 15 Newton meters, which is 15 joules. We've got the work. Let's do another one. So similar to what we've just looked at, we've got a spring giving us a triangular shape on a graph. A spring is being stretched, and as you stretch a spring further, the force required to do it increases. And so we've got this. To figure out what the work done is, we need to find the area, because we can't use work equals force times distance. The force is changing. So work is going to equal the area. Well, the area is going to be given to us by a triangle. So we're going to get 1/2. The base is 2 meters. The the height is 10 newtons. And so what we're going to get here is half times 2 is 1 times 10 is, well, that's just 10 joules of work done. For a spring, the language here, or what we say is that our force is proportional to x. So it's, I don't know if you've seen this kind of language before, either in math or in physics 11. This represents a graph that is directly proportional to x. As x increases, f increases. Springs get weird though, as I've said. If you've ever played with a slinky and you see if you stretch it too far, there. We have a 2 Newton meter spring that goes plastic, is the language for that, at 4 newtons, stretched by it is stretched by 4 meters. So the plastic means that there's no change in the force with the increase of extension. At this point, you've broken your spring, or you've wrecked your slinky. So because we've got an increasing force here, we can't just take work equals force times distance. What we're going to have to do is take the area. But what we've got here is we've got a composite shape that you would have looked at in middle school. We've got a triangle, we've got a square. So here we're going to have the work is equal to the area. But in this case, we're going to have the area the triangle plus the area of the square. Well, the area of the triangle is 1/2 base times height. Half times 2 is 1 times 4 is 4. The area of the square, well, that goes from 2 meters to 4 meters, or it's not actually a square, it's a rectangle because it goes from 2 meters to 4 meters. So this here is 2 meters. It's 4 newtons tall though. So this is going to give us an area of 8 Newton meters, which is going to give us total work done 12 Newton meters, or 12 joules. What happens though if we get something like this? So if I give you something that looks like this, an inverse square force, we're going to look at what these are later when we start talking about gravity and magnetism. When we say and this thing is it's an inverse square force, what that means is you've got a force that's proportional to something that a graph that looks like 1 over x squared. So we're going to see this again, like I said, when we cover gravitation and I want to say electrostatics. The question is, well, what do you do with something like this? Like it's a constantly curving shape or a constantly curving line. It's not like you can find the area under any one of these things. So what we end up doing here is this is where calculus becomes involved. And we say, well, if work is equal to the area, what we want to do is we want to sum up the area over all of our extensions. And so we're going to get an expression that looks like this. If you take an IB math, you'll see that this is the work now is equal to the integral of f dx, where f is the force over some extension. If you've not taken IB math, you have no idea what's going on with calculus, I'm not going to make you do this. All I want to do here is to show you guys how the area is area under a curve is connected to work. In this case, when we have a force times distance graph. And then for those of you who have seen it before or are ready to be exposed to it, let's make the connection with you guys and the knowledge you've got already. So as far as that goes, this is it from... Oh, there, I shouldn't have done that. This is it from this lesson. I'm not going to do any more with you guys on this one. So I'm going to give you the exercises out of this chapter, or out of this lesson rather. I want you guys to look at questions 1, 2, 4, 8, and 9. If I'm not mistaken, 8 and 9... oh yeah, I have to show you problem here with number 8. 1, 2, and 4 are new. 8 and 9 are review of lesson 1. And I do want you to do those to make sure you've got a handle on it. I'm going to show you something here, though. We've got a problem with 8. The answers in the book are actually wrong. All 3 of them. So for number 8, 8.9 newtons should actually be 9.69 newtons. 89 joules should be 96.9 joules. And instead of 13.3 watts, it should be 14.5 watts. So take a look at those, and I'll post some more videos for you guys tomorrow.